Hello students, in this video we'll see how to solve an initial value problem using the Laplace transform. Let's consider y double prime minus 2y prime plus 5y equals 0, together with the two initial conditions, y of 0 equals 2 and y prime of 0 equals negative 4. So we'll solve this problem by taking the Laplace transform on both sides. The Laplace transform of y double prime minus 2y prime plus 5y is the Laplace transform of 0. Now we will use our differentiation rules. Recall that the Laplace transform of the first derivative is s times the Laplace transform of the function minus the function at 0, and the Laplace transform of the second derivative is s squared, the Laplace transform of y, minus s y of 0 minus y prime of 0. Those are my differentiation rules. So let's apply them. We will get, when I Laplace transform the left-hand side of the equation, s squared Laplace transform of y minus s y of 0 minus y prime of 0. Then I'll have a minus 2 times the Laplace transform of y, which is s y tilde of s minus y of 0. And then plus 5 times the Laplace transform of y is the Laplace transform of 0, which is 0. Now I will gather all the terms that have Laplace transforms and all the terms that don't. So first let's simplify these terms over here. This y of 0 term is 2. This y prime term is negative 4. So I'll have a negative 4 or positive 4. And this y of 0 term over here is 2. So we'll simplify and gather like terms. So the terms that have a Laplace transform of y are s squared, then minus 2s, then plus 5. Those are the terms that are multiplying the Laplace transform of y. Then over here I have a negative 2s. Over here I have a negative 4, so that's a positive 4. So I have a positive 4 from this term over here, and I have a negative 2 times negative 2, that's another positive 4, equals 0. So now we will solve for the Laplace transform. This tells me that the Laplace transform of y, by subtracting this to the other side, will be a 2s minus 8 divided by s squared minus 2s plus 5. Now what we'll do is we will complete the square in the denominator. We will write this as 2s minus 8 all over s minus 1 squared plus 4. That step is completing the square. Now at this point we need to use some common Laplace transforms. We know that the Laplace transform of cosine of at is s over s squared plus a squared, and that the Laplace transform of sine of at is a over s squared plus a squared. And we have one more rule that will come in handy, namely the shift rule, that if I have e to the at f of t, this Laplace transforms to f tilde of s minus a. In other words, multiplying a function by e to the at has the effect of shifting the Laplace transform. So now what I'd like to see is I have this s minus 1, so that signals that I'd like to see an s minus 1 on the top and the bottom. So now we'll go back to our Laplace transform. Our Laplace transform can be written in this form as 2s minus 2 divided by s minus 1 squared plus 4. And then I'll have a minus 6 left over, so I'll have a minus 6 over s minus 1 squared plus 4. So now this first term over here is a factor of 2. So this will be 2 times s minus 1 over s minus 1 squared plus 4. And the second term over here, also I can write this as minus 3 and then 2 over s minus 1 quantity squared plus 4. Now I can combine both these rules together to inverse transform. So now if I inverse transform, we will see the first thing inverse transforms to 2. That factor stays outside. Then I have an s minus 1 over s minus 1 plus 2 squared. So this is going to come from a cosine of 2t. So I have an e to the t for my shift of 1, and then a cosine of 2t. And then I'll have a minus 3 times what? This quantity over here. And so by inverse Laplace transform this, we are going to see that a is 2, and I'm shifting the sign of 2t over by e to the t. So I'm going to have an e to the t sine of 2t, and that's the solution to our initial value problem. Thank you very much.